Be live. Maybe. Maybe not. This way here. Just share this on LinkedIn quickly, just in case someone wants to join in. This sound should be okay. Just read this while we posting.
Detecting envelope shapes like squares, trapezoids, and other geometrical figures in time series data can be approached using both fuzzy logic and neural networks. Here are examples of how each method might be applied. Fuzzy logic. Approach. Define fuzzy rules that describe the characteristics of each shape. For instance, a square wave might be defined by its period, amplitude, and sharp transitions. A trapezoid might be characterized by its asymmetrical rise and fall times. Implementation. Create a set of fuzzy rules that capture these characteristics. For instance, a rule might state that if the rise time of a signal is short and the amplitude is within a certain range, then the signal might be a square wave. Advantages. Easier to understand and interpret. Good for situations where precise definitions of shapes are known and can be described in rule-based logic. Neural networks. Approach. Use a neural network, such as a convolutional neural network, CNN, to learn the characteristics of different shapes from a labeled dataset. The dataset should include various examples of each shape under different conditions and noise levels. Implementation. Train the neural network on this dataset, allowing it to learn the features that distinguish each shape. Once trained, the network can classify new unseen data into one of the known shapes. Advantages. Highly effective in complex, noisy environments. You learn subtle distinctions between shapes that might be difficult to capture with rule-based logic. For both methods, it's crucial to have a good representation of the time series data. This might involve pre-processing steps like normalization, noise reduction, or feature extraction to make the characteristics of each shape more distinguishable.
Right. So we'll be doing neural nets and fuzzy logic today. Just some basic examples. We had them running on a website quite a while back. I have to bring them back at this old descriptions for them. These are the only two tools that are not actually working on the website. So why those PHP files loading forever. Right, so I have some description in them, which we will use. There's some old videos describing how they used to work, so we'll be bringing them back. They used to be LabVIEW, and now we're doing it all in Python. So there's these two tools. Let's quickly do the videos there. To just a reminder what they used to be. So this one just having this noisy sinusoid, and it's doing prediction of what the signal will look like, essentially future prediction. And this one does detection, so it has this various shapes of essentially what could be time series envelopes of a signal, and it's detecting the shape. And yes, there's can add a noise onto it, so it shows you how worse it gets with increased amount of noise. So obviously the detection is obviously easier than prediction generally. just pop all of this. Should we use GitHub Copilot or ChatGPT in OpenAI? I mean, GitHub Copilot meant to be using ChatGPT anyway. Okay, let's start with something. So we'll use that the last tool that we have inside is the EEG into music conversion. I'll just use that as a template. Let's fetch the names. This one used to be called. Rename this into fuzzy logic, which we already have. Get that HTML. We just need to extract the text out of it. Otherwise, there's not much, nothing much interesting in it. So logic. Let's do the info. Yeah, we use the same structure. For the file, we currently, we won't use any real data for this one. Yeah, we'll keep it as a Flask application. We deploy it, hopefully, when it does something useful. We mainly, after all this, yes, we have those shapes. Have those shapes. Square left trapezoid, and we'll try to do detection of those. Essentially have the input and output, and we deploy an Apache server. And we can delete that quickly. So there's some organizational stuff. It won't take too long. Okay, we can delete that, rename this to fuzzy logic, so the page will remain the same. Yeah, so this is without this is with noise reduced. Templates. Let's quickly pop this into GPT 4. Why did it decide updating? Stop that. Remove those. So it's clear that it's a Flask application.
Waveform shapes. The FLS is tasked with identifying various waveforms like square, left, right trapezoids, left, right triangles, and hexagons. Noise impact. As the noise amplitude varies, the detection error of the FLS also changes. Interestingly, medium noise levels result in more misidentifications than higher noise levels. This could be due to the way noise interacts with the specific features the FLS uses to identify shapes. Data points usage. The FLS utilizes only 6 data points from top and bottom scanners to identify the waveforms. This limited data input might be a factor in the performance variability with noise.
Right, but we don't mind you improving it. Originally it was LabVIEW example, and LabVIEW does all this industrial engineering, manufacturing stuff, so it was an example of different boxes, different shapes on a conveyor belt, and a bunch of limited number of sensors detecting the shape of the box. Don't have to do it that way, we can improve on it. Let's try the image thing. So if we had the quality is reduced, can go up to 4K or whatever. Oh, we don't need 4K. 1080p should be more than enough. Just give us an image. We want to pop this image into GPT-4. Why is it not? All right. So we have this. Let's do web print screen. From here to there. So that's what this is what the application front panel should look like. Yep.
Based on the screenshot you've provided, it appears to be the front panel of a software application designed to analyze waveforms using fuzzy logic. The interface has a section for selecting the input wave, shape, and adjusting the noise amplitude, which suggests the application is set up to test the robustness of waveform identification under different noise conditions. On the right side, it displays the output wave, which is the detected shape, along with statistical data like % detection error and % unknown, indicating the performance of the fuzzy logic system in real time. The graph on the left seems to show the selected waveform, in this case, a left triangle, with a shaded area representing the amplitude over time. The graph on the right shows the performance metrics, where the red line likely represents the percentage of detection error and the blue line represents the percentage of times the waveform was not identified at all, unknown. This type of application can be useful for demonstrating the principles of fuzzy logic in signal processing and for educational purposes, such as in A.
I also saved this image. The drop downs as expected. Now we have the actual HTML and template folder. Start using GitHub Copilot in a sec. Just need the template. Leave all the header stuff. We need that as well. From container. It's not really a waveform analysis, but it's something we'll get into the fuzzy logic in a sec. I have a CSS for it. Let's do format this document. Read this quickly.
The drop-down menus, less than select greater than, are used to select the input and output waveform types. The range slider, less than input type equals range, allows for the adjustment of the noise amplitude. Placeholder divs with the class graph are where you would integrate the plotting library, like Plotly, to display the waveform and the detection error graphs. The CSS and JavaScript files are referenced, but not included here. You would need to create them to handle the styling and functionality, such as responding to user input and updating the graphs. This HTML template is a starting point and would with back-end logic to process the data, generate the graphs, and update the statistics in real time.
I want to write the Flask application template. Yes, the form analysis up. This goes into this simple Flask application. Okay, we don't need all that. Let's run this quickly. Probably won't run. It is running, surprisingly. Okay. It's a good start, but it's the JavaScript. Yeah, I'll rename it as main. Main.js. Are you suggesting to have in it?
Creating a main.js file for your Flask app involves writing JavaScript code to handle user interactions, send AJAX requests to the Flask backend, and update the web page dynamically with the results. Below is an example of what the main.js file might look like.
Okay, we're missing quite a bit. Some papers that the ChatGPT plugin, this plugin called Scholar AI, found time series prediction of driving motion scenarios using. Yeah, I don't know about that. Interval type 2 fuzzy aggregation approach combining multiple neural networks, clustering prediction time series. Yeah, it's a lot of robotics, time series prediction, and anomaly detection with recurrent spiking networks. Let's check if these links are legit at all. Da-da-da-da. IEG.org is a legit website. Seem to load something. It's a legit. Yeah, it's a conference. Great. This is what Google Scholar gave. Yeah, obviously forecasting financial time series. It's not quite the topic of my YouTube channel, but yeah, I'm sure this will get a lot of views. Yeah, I'm interested in how they did the comparison between the two. How do they even measure performance? I mean, you can do it with past data. Currently, we're just sticking to prediction quickly. I have some template for the JavaScript.
We add event-lessness to the input waveform selection and the noise amplitude slider. When the user changes the selection or the slider's value, the analyze waveform function is called. The analyze waveform function gathers the input data and sends it to the Flask backend via a post request turn analyze route, which you will need to implement in your app.py. The server is expected to process this data and return JSON with the output wave, detection error, and unknown percentage, which are then used to update the page. Remember, this is a basic example. Depending on the actual processing and data structure you use, you might need to adapt the JavaScript code accordingly. Also, to make this work, you need to set up the corresponding backend route in Flask to handle the post request and perform the analysis.
I'm having trouble finding the style CSS file. Actually, should be two of those. Start the application. It's a bunch of errors. It's the wrong bold and aim. Oh, this one's okay. Logo's okay. Script.js. Get some static. Go main.js. It's loading forever from a CD and loading Plotly. It's still running. What's it doing? Yeah, Plotly loading forever. Why? Wow, forever. What's that H? Yeah, let it rest for a while. I don't know why it's loading for so long, but and let it be. Can you write the HTML description for this web application? Yep. Why? So for that, write description for this web application in HTML format. Okay, to remove some of these descriptions. There's no data source because it's generated within the app. Get rid of this section for now. Right, so the main problem is that we do not get an error. Let's have a template somewhere. Yeah, I can update the graphs here. How to update the graphs. Using charts, charts.js. And we're using Plotly. Using Plotly instead of charts.js. How do I add the charts? Wait, how many? There should be just the one, isn't it? So we're already including Plotly. Yes, it is a great tool. Thank you. Input graph, output graph. That's right. So there are two of them. I need to make sure they actually the noise amplitude is important. It's the noise. So JavaScript should take this noise amplitude and generate a waveform out of it. It should have a basic shape based on the input window. How do we make sure we have the input chart to be the waveform with the noise? Oh, come on. Be the waveform with noise amplitude embedded. Added to the signal. Envelope. Let's do things one by one. Have the signal being plotted? No. Is this? I don't even know. Is this JavaScript or Python? And yes, ideally we wanna how to modify this file with the recent changes. State input graph that creates a plotly graph in the input graph division. Don't have an input graph division. Why does it keeps jumping around between JavaScript and Python? Pretty sure we have NumPy installed. Thank you, Namori. It's a pleasure having someone live. So it feels like I'm actually talking to a person. Yeah, trying to create an application. It looks like this. We had it running before on the site, but it was LabVIEW. Now it's not running anymore. It's basically selecting a shape of a signal, adding noise to it, and there's a detection algorithm, in this case a fuzzy logic algorithm, that is used to detect the original signal. And obviously with increased noise it becomes harder to detect the signal. So currently we are replicating this in Python, having a few problems, mainly with this JavaScript code. So we need to update our Python script as well. We're still kind of in a template stage. Right, so we have, yes, we are doing a Flask application. We have an index HTML, have a method that will be called using a post HTML request called analyze, and it will give you the result. And yes, the debug is true. It's looking good. Now, where's this actual signal coming from? We have this template. Let's ask the same question, how to update. Considering we should have the data actually coming from the backend, from Python. Hopefully it will fix this for us. So we have elements, getting elements from the HTML, data output wave, signal, well, what we currently have doesn't work, so we might as well replace it. Right, the error went away. The error went away. This, by the way, not the EEG. This will be more basic stuff. Let's check the. Don't tell me we have 56 errors. This will be like a fake EEG. It's still time series data. It's loading forever. So we're selecting as if, I mean, later we can add the other shapes to it as well. That might be more EEG relevant, like a spike. Can have an envelope of a spike or slow wave EEG. And this particular tool is using fuzzy logic to try and detect this signal. Currently, alright, we have to update this HTML because we actually need the charts in it. We're actually using GitHub Copilot, which meant to be GPT-4. Okay, no, I meant with the charts. We need the charts visible. We have charts. No. It's the ID. Output wave, input wave. No, the input wave is already there. No, that's the drop-down menu. We actually need the chart as well. Chart. Have noise output. Yeah, the input graph. Input graph. So we do have the input graph and output graph, but we don't see them. Where are they? Panel graphs. Okay. It's either they are empty. Now, the one thing that the GitHub Copilot cannot do, as opposed to GPT-4, is hold a larger context for more files. So the question is, if we supposedly, in theory, we should be able to do it using this workspace. We ask questions here. It should take look at all the open files in theory. How do we, the input and output graphs are not displaying anything. How do we fix this? So it's collecting workspace structure, detecting which workspace information to collect. Supposedly it is looking at multiple files, hopefully. But before this stuff was giving us an error. And by the time it takes for this to do this detection, it feels like I'm gonna get another error. Because it's essentially GitHub Copilot doesn't know where to look in the project. Well, while we wait, what was the question? Following up on the message on LinkedIn, I plan to convert the EEG files to audio for my dissertation research. I hope you are willing to help. My best regards. Well, yeah, happy to help, but I won't be doing your dissertation for you. So any specific questions are more than welcome. Yeah, so getting this encoded in there while deciding what workspace information to collect. Length. I guess the issue is length. So it's too many lines of code for essentially GitHub Copilot to hold this information. And I know for a fact that GPT-4 interface can handle all like essentially more lines of code. So let's try input graph. Obviously we need the JavaScript for this. Yeah, so can actually select all JavaScript, the input and output graphs and not display anything. How do we fix that? And now it's actually looking at the 77 lines of JavaScript code. Plotly library is correctly imported. Yeah, Plotly library is loading forever. Don't know why. Let's check if it's imported. Check if the data is there. I suspect there's no data. Check noisy signal. Update input graph. Log noisy signal to console. Let's log this quickly. See if it's not empty. Messages. Generate signal is not defined. Generate signal is not defined. Never understand this main.js 4222, 4222. Which one is it? 42. Generate signals not defined. I'm not having that labeled by the linter. Can you solve this for us? It's a template, isn't it? Need to replace this. Yeah, this should be a function. Yeah, it's all templates so far. Let's format document, generate signal. That error should go away. Okay, there's something wrong with the loading time. Where's the network? No, those errors are actually okay. Yeah, it's loading the plotly. Okay. Yeah. So we do have the data. We do have some noisy data. Looks like it's overlaid on top of a sinusoid. Yeah, we can add noise, just great. And the output is not doing anything because we don't have that functionality yet. Yeah, there's a lot of problems. Where do we log? You can remove this logging. Maybe it will run faster. Can we quickly fix? No, I don't know if I can fix it. I don't remember having this issue before. But this CDN seems to be loading forever. Loading forever. Let's see what it's if it's suggesting anything. Well, forever, it's eventually loading, but it's way too long. And it's meant to be a mini version of it as well. Check your internet connection. Actually, I'm dropping frames in my stream. Okay. Not dropping them anymore, but I already dropped like thousands frames. That's not cool. Try different CDN. It's actually, well, I mean, if this one's working. Yeah, I'll try it when not streaming, supposedly. Taking too much bandwidth, internet connection while streaming. And by the way, yes, it is affecting my server as well. So the biomedical.com website might be slow. Okay. The other problem is obviously the output. Yeah, the, the output shouldn't be a selection. It definitely shouldn't be a drop-down menu. It should be an output, right? So let's change that. The output should not be an input, so it should not be a drop-down menu. It should just display the output. Place this code. And note that the web display has a paragraph. You can update the text of this paragraph to JavaScript code using inner text property. Okay. I mean, it could be an input only if we are training, but we are not training at the moment. Should we change it? Yes. Label for output. Yes, we can change that. This output wave. Element by ID. Let's get rid of that for a sec. Data output wave selection statistic, update output data. Yeah, output data is not updated. Um, yeah, we need to know how to control output wave. Hey, we need to update for output wave. So in HTML, we have that, okay. And in JavaScript, update output data. That won't work, but okay. Because we don't actually have the output data. We also don't need this constant. Yeah, so the output should be displayed as text. That won't work, would it? Output wave. Okay, we actually need the input waves to work properly. Were we generating the functions in Python code or JavaScript? It's okay to generate them in JavaScript. I want to do as much as possible on the front end so my server is not overloaded. Update this with actual waveforms. And we can add the sinusoids as well. A square works. What did they have? A triangle. Default is still sine wave. Okay. A case. Left trapezoid. Just this, that. Is it case sensitive? Must be. Doesn't work. Square works, and there is no output. There is no output. Do we have update? Don't have those functions, do we? No. Graph is updating. I don't know what you're talking about. Okay, go figure. Go figure. So we have the noise, everything that doesn't work ends up being a sinusoid, and there's no output. There is no output. The analyze doesn't do anything anymore, does it? Yeah, that's just a mock-up. Generate signal, add noise, analyze signal, calculate detection error, calculate unknown percentage. That sounds much better, doesn't it? Why couldn't you just do it to begin with? Not dropping frames anymore in my stream, but the JavaScript is loading forever. Output wave is empty. Detection error is always 0%. Unknown is always 0. Oh, really? Really? I'll understand the context. Seems like you want to display the output wave detection error and unknown percentages or HTML. HTML. Let's check HTML control, output wave. You already have that. Detection. Okay. Date output in JavaScript function. Do we have this function? Okay, it should be better. Does that make sense? Having an error. In JavaScript, that's 67. That's where the error is from. Add noise. Let's see. Yeah, those are just templates. That doesn't work. Let's do actual code to calculate a no percentage. It should be signal. Noise signal should be input and output. And no. It should be using fuzzy logic. Yeah, that's right. Okay, Python code should do a fuzzy logic. A Python fuzzy logic library. Yeah, this is not quite right, it's just an example. That's a good start. To install this library. We install it globally. too long. Something. Quickly. Have been almost 2 hours, and we haven't even started with the actually designing the fuzzy logic. Give me a number. So it's not noisy, it came 2.5. It's noisy, it came something else. Yeah, we need to change. Yeah, so the one good thing about LabVIEW was not using it anymore, mainly because of the cost of the license. But it had the toolkit for designing fuzzy logic, so these membership functions. So not sure how we're gonna do it now. Essentially, it's taking out the features from the signal. So one thing is for sure, output wave should detect input wave, so the values should be the same. can simply return the input wave. Yes, we do want to perform the fuzzy logic. No, that would not do it.
Main content. Your main content section includes the application description and placeholders for additional information about how it works, getting started, features, key insights, technical details, and a closing note. Flask variables. The use of Flask's URL_ for in script tags is correct and ensures that the paths to your static files remain valid even if the structure of your application changes. It gets references to various HTML elements that it needs to interact with. It defines functions to update the output statistics and the input waveform graph. It contains a generate signal function to create different types of waveforms based on the selection. It defines an analyze waveform function that generates a noisy signal based on the selected waveform and noise amplitude. Updates the input graph with the noisy signal. Sends the waveform data to the server for analysis via a post request. It has event listeners set up for when the user changes the input waveform type or the noise amplitude. It performs an initial analysis when the page loads. Here are some points for improvement and clarification. The generate signal function includes cases for different types of waveforms, but it seems incomplete. You should ensure all waveform types in the select element have corresponding cases in this function. The noisy signal generation uses a simple random function for noise. Depending on your requirements, you might want to use a more sophisticated noise model. The fetch call sends data to the analyze endpoint, which you need to implement on your server side in Flask to accept the post request and return the analysis results. The comment, replace with your function to generate the signal, suggests that you should implement a more robust signal generation function based on your application's needs. Make sure to handle errors appropriately on the server side and provide feedback to the user in case something goes wrong. After fetching the analysis results, you should update not only the statistics but also the output graph if needed. This part of the code is indicated by the comment. You would also call functions here to update the graphs. Ensure you include appropriate error handling for network errors or server-side issues. Lastly, ensure the script is linked correctly to your HTML and that the server-side processing script, app.py, is prepared to handle the requests and serve the necessary responses. This script is client-side JavaScript and should be linked to your Flask application's HTML template so that it can control the behavior of the web page in response to user inputs. Make sure to test this script thoroughly to ensure it behaves as expected. This Flask application serves as the back-end for the waveform analysis tool. It defines several routes and functions to process the waveform data received from the client side and returns the analysis results. Here's a breakdown of the application's components and some suggestions for improvement. Flask routes. The home route serves the index, HTML template, signal generation and analysis. The generate_signal function should create a signal based on the input_wave parameter. You will need to replace the placeholder code with the actual signal generation logic. The add_noise function adds Gaussian noise to the signal based on the noise_amplitude provided. Fuzzy logic analysis. The analyze_signal function is intended to perform the fuzzy logic analysis on the noisy signal. The fuzzy_logic function is where you define your fuzzy membership functions and rules. This function uses the skfuzzy library to apply fuzzy logic operations on the noisy signal. The example provided is very basic and should be tailored to match the specific fuzzy logic operations that are appropriate for your application. The calculate_detection_error and calculate_unknown_percentage functions are placeholders to calculate the error metrics. You need to replace these with actual calculations that compare the original signal to the noisy signal and determine how well your fuzzy logic analysis is performing. Response. The analyze route returns a JSON response containing the original input wave type, noise amplitude, and the analysis results, including the output wave, detection error, and unknown percentage. Suggestions for improvement. Implement the actual signal generation logic in generate_signal for different wave types. The fuzzy_logic function currently only demonstrates how to use the skfuzzy library and does not relate to the actual waveform analysis. You need to define the fuzzy sets and rules that correlate to the specific features of the waveforms you're analyzing. Ensure that calculate_detection_error and calculate_unknown_percentage are properly implemented to reflect the accuracy of the fuzzy logic analysis. Error handling. Add appropriate error handling throughout your application to manage and respond to any unexpected behavior or errors during the processing. Validation. Ensure that the input data from the client is validated before processing to prevent any potential issues or security vulnerabilities. Before deploying the application, you'll need to test all these components to ensure they work together as expected and provide accurate results based on the input data. To implement the generate_signal function for different wave types, you will need to define how each waveform is generated. Let's assume that you want to create different waveforms with a fixed length of 100 data points. Here's how you might implement the generate_signal function for square, left triangle, right triangle, and left trapezoid waveforms. This generate_signal function defines the signal generation for several waveform types. Square, a basic square wave oscillating between -1 and 1. Left triangle, a triangle wave that ramps up from -1 to 1. Right triangle, a triangle wave that ramps down from 1 to -1. Left trapezoid, a trapezoid wave with a ramp up, sustained high level, and sudden drop. Right trapezoid, a trapezoid wave with a sustained high level, a ramp down, and a sustained low level. Hexagon, a waveform with sections to create a hexagon shape. Each waveform is generated based on the time vector t, which goes from 0 to 1 over the length of the signal. The NP, piecewise function is particularly useful for generating waveforms like the trapezoid and hexagon, as it allows you to define different functions over different intervals of t. Remember to test each waveform to ensure they are being generated correctly. You might need to adjust the parameters and conditions to match the exact shapes you want.
issues with the labels. Should have left them as they were. Like this one here. Oops. No. Control Shift C. Always forget. So it's giving me the sinusoid. Don't know why. Right, so it should have been okay. Yeah, we need to the fuzzy rules is more than just the template. Yeah, the GPT-4 interface on OpenAI is so much better. Can actually hold on
Designing a fuzzy
larger
logic function,
context.
fuzzy_logic, for waveform analysis requires defining fuzzy sets and rules that are tailored to the specific characteristics of the waveforms you are trying to analyze. You need to identify key features of each waveform that can be used to differentiate them. Let's go through a hypothetical setup for a fuzzy logic system that distinguishes between a square, triangle, and trapezoid wave based on features such as symmetry and peak sharpness. Firstly, you would define the universe of discourse and membership functions for each feature. For simplicity, let's assume we're looking at two features, symmetry and peak_sharpness. Here's an outline of what the fuzzy_logic function could look like.
So originally I think it was looking at 3 sensors. But this example is better because it's actually taking out the features.
In this function, the extract_symmetry_feature and extract_peak_sharpness_feature functions would contain the actual logic to calculate the symmetry and peak sharpness of a signal. These are just placeholders and need to be replaced with actual feature extraction logic. The fuzzy sets are defined for low and high values of each feature. The rules are then applied to these membership functions based on the logic you decide. In this example, we assume a square wave has high symmetry and low peak sharpness, etc. Finally, the aggregated membership function is defuzzified to make a crisp classification decision. Please note that the above is a simplified example. An actual feature extraction and fuzzy logic implementation will require a deeper understanding of the signal characteristics and the appropriate fuzzy logic design. You will need to adjust the membership function parameters and the rules based on the actual features of the waveforms you're analyzing.
Well, this is so much better than what the GitHub Copilot gave, that's for sure. It actually understands way more of the context of what is it we're trying to do. Still having some technical issues with the tool itself. It actually became worse. The output.
To properly implement the calculate_detection_error and calculate_unknown_percentage functions, you need to define a methodology to quantify the performance of your fuzzy logic analysis. These functions should compare the output of your fuzzy logic system, the classified waveform type, against the expected results, the actual waveform type, and calculate relevant metrics. Here's an example of how these functions might be implemented. The detection error can be measured as the percentage of times the fuzzy logic system misclassifies the waveform type. The unknown percentage could be the percentage of waveforms that the system can classify confidently. In these functions, original_wave and classified_wave are lists containing the types of each waveform in the same order. The calculate_detection_error function compares each pair of original and classified wave types and counts mismatches. The calculate_unknown_percentage function counts how many times the classified wave is marked as unknown. Note: ensure that the output of your fuzzy logic analysis, the classified_wave list, and the ground truth data, the original_wave list, are correctly aligned and have the same length. This approach assumes that you have a labeled dataset or a mechanism to generate ground truth labels for your waveforms. If your application doesn't provide such labels, you may need to adjust this approach accordingly.
This output wave should be a text, obviously. You get a lot of errors. Let's clear this quickly. Don't trust the GitHub Copilot as much as I trust GPT-4. Just the implementation of it.
The error message you're encountering indicates a mismatch in the lengths of the arrays passed to the defuzz function in your fuzzy_logic method. Specifically, the symmetry_universe array and the aggregated fuzzy membership function array need to have the same length. Here are the steps to troubleshoot and resolve this issue. Verify array lengths. Ensure that the symmetry_universe array and the aggregated array passed to the defuzz function have the same length. This is crucial for the fuzzy logic library to perform defuzzification correctly. Check membership function definitions. Review how you have defined the fuzzy membership functions, like mf_symmetry_low, mf_symmetry_high, etc., and ensure they match the universe of discourse, symmetry_universe and peak_sharpness_universe. Each membership function's definition should use the respective universe array as its base. Review aggregation step. When aggregating the rules to form the aggregated array, make sure the operation doesn't inadvertently change the length of the array. The aggregation should result in an array with the same length as the symmetry_universe and peak_sharpness_universe. Add print statements before the defuzz line to print the lengths of the arrays. For example, Python copy code print, length of symmetry_universe, len, symmetry_universe. Print, length of aggregated, len, aggregated. Inspect the arrays to see if their lengths indeed match. Example correction. If the aggregated array is shorter or longer than the symmetry_universe, you need to revise how it's being created. Make sure that all operations leading up to its creation maintain the array length consistent with that of the universe array. Ensure that the universe arrays, symmetry_universe, peak_sharpness_universe, span the entire range of possible values for each feature. Make sure the membership functions, mf_symmetry_low, mf_symmetry_high, etc., are defined correctly over their respective universe arrays. By carefully reviewing and adjusting these aspects of your code, you should be able to resolve the length mismatch issue and ensure that your fuzzy logic analysis works correctly.
So the length of a symmetry universe is 100. problem with this array. For this, I get it's a problem that the array doesn't have a length in it. It's actually an error message I didn't see. It's a float 64. Anyway, we'll have to troubleshoot it next time. I'll see you later. Bye.